Hello, I'm Bill Kinney, and this is the fourth part of my series of videos about multivariable calculus, also the fourth part in my sub-series about graphing and calculations with parametric curves. In this video we're going to look at parametric curves defined by basic trigonometric functions. We'll talk about eliminating the parameter in such a situation and find the distance traveled and the speed, assuming it's a constant speed. So here's the situation. We've got a person walking in an xy coordinate plane with distance measured in meters and time in seconds. We've got a system of parametric equations that's describing this motion using basic trig functions. F of t, the x coordinate, is going to be the cosine of t. G of t, the y coordinate, is going to be the sine of t, and t is going to vary from 0 to 2 pi. I would strongly encourage you to take the time to use your calculator or Mathematica or whatever program you have to plot this system of parametric equations based on what I've told you or what you've learned otherwise about these equations and how to plot them. I will now use Mathematica to plot them quickly. I will go through the Mathematica Code pretty quickly. If you want to see me go through this code more slowly, you should watch the first 3 videos if you haven't. So I will graph the path of the person with a command called parametric plot and also manipulate. I will eliminate the parameter to find an xy equation of the path. Describe the shape of the path if possible, the distance traveled and speed if possible. Assuming the speed is constant, we'll try to figure out what it is. Finally, we'll experiment with modifications to these functions to see what kinds of things can happen when you modify these equations. Interesting things can happen. So I will quickly type in the Mathematica Code to do the graphing here right away. Alright, so f of t is going to be, oops, losing my place here, sorry about that. F of t is going to be cosine of t, g of t is sine t, c of t is the point valued function f of t comma g of t as a list in Mathematica. I'm now going to make an animation of a plot of this. I'm going to include what I did on the last video where I also mark a point at the location of the person using list plot, and I need to combine the graphics that come with parametric plot and list plot using something called show. Video number 3 goes through that in more detail. I will go through that quickly here. And all at once I'm going to use a manipulate, then a show, and inside the show is going to be both a parametric plot and a list plot. The parametric plot, I'm plotting c of t. T goes from 0 to b, where b is my animation parameter for the manipulate. I'll make it magenta this time for some variety. Thick magenta. List plot plots the dot at the point c of b as b changes. I use a t here. T goes from 0 to b because I want it to trace out the entire curve from 0 to b. But here I'm just graphing a dot, the point where the person is, so I need the b, the animation parameter, in there. Styling option, plot style, thick, comma, point, the c, excuse me, black, comma, point size, 0.02 is the one I typically use in there. And then I need some extra formatting commands within the show but outside the parametric plot and list plot. So right after this list plot I put a comma and I put my formatting commands like the plot range. I want that to stay constant. I'm going to pick -2 to 2 in both the x and y directions. I want to label the axes. Axes label x and y, just like always. I will make these bigger. And finally, I need an axis origin in here to keep that fixed. Kind of a quirk of Mathematica that doesn't always stay fixed. Alright, we're ready to see the motion. Here it is. I hope you got this when you tried it by hand. This is circular motion. It does seem to be at a constant speed, and in fact that is true. Let's look at answering these other questions now. So we graph the path of the person. How do you eliminate the parameter to find an xy equation of the path? Well, you could guess it based on the fact that that graph did look like the unit circle, circle of radius 1 centered at the origin. Why is that the case? Why, in fact, that is true. Why is it always on the unit circle? The way to eliminate the parameter here, the best way, is to realize that we can really eliminate the parameter by realizing that cos squared t plus sine squared t is always equal to 1. That's a fundamental trigonometric identity, sometimes called a Pythagorean identity because it comes from the Pythagorean theorem. The fact that this equation is true for all t implies that the path is along the unit circle with equation x squared plus y squared equals 1. Because when you replace x with cosine of t and y with sine of t, you get exactly this expression right here, cos squared t plus sine squared t. And you know that always equals 1. That's something you learn from trigonometry no matter what t is. So it always is on the unit circle. It actually does trace out the unit circle completely as t goes from 0 to 2 pi. And in fact, you should know that based on the unit circle definition of cosine and sine. That's what we're really using here to trace the unit circle. In effect, this is going to be true by the basic definition of the cosine and sine functions in terms of the unit circle. What's the shape of the path? It's a circle. Again, the circle of radius 1 centered at the origin, also called the unit circle. What's the distance traveled? Distance is going to be the circumference of the circle. That'll be 2 pi times the radius, but the radius is 1, so the answer is 2 pi meters. Is the speed constant? I said yes. It should have looked like it was. I'm not going to prove it is here at the moment. In a future video soon I will prove that the speed is constant. Yes, the speed is constant, and it is the distance traveled divided by the time elapsed. 2 pi meters divided by 2 pi seconds. Meters divided by 2 pi seconds elapsed. That'll be 1 meter per second. That is the constant speed. Finally, we will experiment with some other kinds of parametric curves you can make based on this. Let me just copy and paste this part here. For example, if you want the curve to be traced out, say, 3 times as fast, you can replace the t here with a 3t, and the b here with a 3b. This will trace out still the unit circle, and I would encourage you to think about why, but now 3 times as fast. As t goes from 0 to 2 pi, the unit circle will be traversed counterclockwise 3 times. It's going 3 times faster, 1, 2, 3 counterclockwise revolutions there as t goes from 0 to 2 pi. The distance traveled would be 6 pi, and the time of travel would still be 2 pi, so the speed now would be 3 meters per second. Another thing you can do is you can replace the t's with negative t's, and the b with negative b, and that will be a clockwise motion instead of a counterclockwise motion. I would encourage you to think about why that happens. One more interesting thing you can do with this particular example, there's lots you can do, but here's something else I'm going to do. I'm going to make it start at the top of the circle instead of the right side point on the circle at its positive y-intercept. Replace t with t plus pi over 2, and replace b with b plus pi over 2, and that will start you at the top of the circle at the positive y-intercept instead of the positive x-intercept. We're still going counterclockwise here. Here's your exercise to work on now. It's very similar. I will tell you, as I've typically been doing with these exercises, this is supposed to be an exercise, forgot to change that word. What I've typically been doing with these exercises is making them a little bit more difficult than my examples, and this is indeed a little bit more difficult. I will in fact give you the hint that the distance traveled cannot be calculated exactly. based on what you know. The speed is not constant, so you won't be able to find the speed. Here's what you can do to answer the questions though. This path is actually an ellipse rather than a circle. The fact that the coefficients of the cosine and sine are different is what makes that be an ellipse, an oval rather than a circle. What ellipse is it? It's this, the one that's defined by this equation here. It comes from this fact here, that that's true no matter what t is. Turns out, though you wouldn't know this ahead of time, that the circumference of the ellipse cannot be found in terms of what are called elementary functions. Functions you're used to is basically what that means. But it does turn out to be 15.87 meters. You could try to estimate that visually, though I'm sure you couldn't get it to that kind of precision. The speed is not constant, which should seem reasonable as you look at this animation. I'll let you look at it once again. In fact, the speed is faster near the top and the bottom than it is near the left and the right. That's a little hard to tell here because it's not a real big difference. And you can experiment. You can double the speed or triple the speed. Here's double the speed. You can make it just like before, go clockwise instead of counterclockwise. And we also could start this one at the top or the bottom or wherever we want to start by doing basically a shift of the input to the c function. And that'll be the end of this video.